Hello, my name is Alexander and you're on the DP Labs channel. Today I want to tell you about preparing an engine for testing on a dynamometer. Since we have a hub motor, there is no shaft, so there's simply nothing to measure the power from. What does the test bench actually look like? There's a sensor with a shaft which needs to be connected to another shaft via a coupling, and that's how you measure the power. A hub motor simply doesn't have anything like that. To solve this problem, we decided to come up with an improvised adapter. For this, we used a chain drive, meaning two sprockets, one on the hub motor, the other on the shaft, and then this shaft is connected to the sensor via a coupling. It's all pretty simple. To make this as quickly and easily as possible, I decided to use laser cutting for the main structure, so everything is made from 5mm sheet metal. And some elements like the bearing mounts and these kinds of adapters I just milled out of duralumin. The sprockets themselves are also made from 5mm steel, also cut with a laser. Then they go on the lathe for precise machining in order to get the correct tooth shape. Here is what the construction process looks like. Here's the tensioner. I don't know how well it's actually going to work. Honestly, I've actually never worked with a chain drive before. I hope everything works out. Besides the engine itself, there will also be several other important components involved in the tests. That's the battery, the controller, and the throttle handle, all of which we'll use to control it. First up is the battery. This is a fresh build for a new scooter. It uses these kinds of cells. They're lithium ion with an NMC cathode. These particular cells have a capacity of 80 amp hours. The whole pack, 22 cells, so that's 22S. If I'm not mistaken, that's about 6.5 kilowatt hours. If I'm wrong, I'm sure someone will correct me in the comments. This battery was built for the scooter with a good margin. It can easily deliver 300 amps without any issues. For a scooter, that's literally just a few seconds during acceleration. It can also be charged very quickly. It supports a charging current of 1C, meaning it can be fully charged in an hour. Now let's talk more about the controllers. I decided to do a quick comparison right on the test bench. I have two different controllers. One of them is the one that is specifically used on the scooter, and the other is a fairly common type of controller that's used in all sorts of other electric vehicles, including the titanium kibitka. It also accelerates too. Hello, let's use our brains. We're heading to the disco. We have a Kelly, a Chinese controller, model KLS 72701, 72 volts, 700 phase amps. And the second controller, which is used on the scooter, is from a domestic manufacturer called Yadranaya Electronics. The controller has a peak power of 27 kilowatts and a nominal power of 10 kilowatts. Here, the maximum phase current is only 500 amperes and the battery current is 300 amperes. I couldn't find a detailed specification for the Kelly. Unfortunately, apart from the 700A phase current, I don't have any other specs. The 700A phase current is only for a short period. According to the specs, it can deliver that for just 20 seconds. For continuous operation, it can deliver 280 amps. This controller weighs 1.1 kilograms. This controller weighs over 5 kilograms. A bit more detail about the nuclear controller. It is completely sealed, filled with compound, and absolutely not afraid of moisture. On the end, it has outputs for the phase wires, plus and minus. There are outputs for the Hall sensors and the temperature sensor. And one more wire connects to the display. There are only 5 wires in total. Information exchange takes place via the CAN bus. This is a wonderful display from which you control and configure the controller. All the necessary information is also shown on the display. Speed, battery charge, remaining range, and everything else. This little device here can also be purchased as an accessory for the controller. This is the microlight expansion board. It allows you to control various consumers, lighting equipment, brake lights, and headlights. I use it specifically to control the brake lights, headlights, and the cooling pump. It connects to the controller via the CAN bus in exactly the same way. And all of the settings are done directly from this display. The board itself has several different power outputs that can be individually controlled. So you can easily program these buttons on the display to control various things, or alternatively, you can connect a bunch of other different buttons, which is exactly what I plan to do. And you can program absolutely any functions you wish to them. In other words, all the buttons are fully programmable. To control the motor, I'll be using a throttle handle of my own making. I just took a ready-made one from a scooter I had in stock. Unfortunately, we didn't have any finished triggers available, or rather, not the polished finalized ones. So I took an unpolished one and put all the necessary internals into it myself. Why are we making it ourselves? Including throttle triggers with button blocks. Just for comparison, I'll show you a Chinese one. Everything I tried to find ready-made basically comes down to the same principle. It's this kind of plastic thing, without a bearing, just running on grease, with plastic rubbing against plastic. When your device has a lot of power, you really want to control and fine-tune the force as precisely as possible. That's why I wanted to install a high-quality bearing, so that everything would be really smooth and precise. The grip itself is of course standard, but I calculated all the angles relative to this protrusion, the throttle trigger, to suit myself, so it would be comfortable for me. The harder you press, the firmer the grip. And the reason I actually like the throttle trigger is because no matter what position your wrist is in, you can always control the clamping force with maximum precision. I want to connect the throttle handle with buttons to the display itself to the controller, and the controller directly to the battery, perform the initial setup of the throttle handle, and upload new firmware to the controller. I just went to the manufacturer's website, and it turns out that a new update was released on May 7th. So let's take the display. We connect the throttle handle to the system. The throttle trigger itself is actually separate from the main handle, and there's also a power button located right here. So in total, we have one ground wire and 3 signal wires. In theory, you could even take the ground directly from the throttle handle itself, but then there would be one extra wire left over. Now I want to connect the controller to the battery in order to power it up and perform the initial setup process. First, I take the negative terminal of the battery and simply connect it with a screw, making sure it is secure. There's no voltage present here at this point, so I can safely establish a connection. Just in case, let's insulate the positive terminal. Everything is lying far apart here, so it's pretty hard to short anything. I'm connecting the cells together. So, you want to connect the positive terminal from this one to the negative terminal of that one, and then connect this one to that one as well. Now, the controller actually hasn't been turned on or powered up for a very long time. Most likely, not since it was originally manufactured, so there will probably be a noticeable spark when the capacitors begin to charge up for the first time. Whoa, that was really quite serious. So, do you think the controller will actually turn on? Oh, it worked, just as we hoped. The battery is currently at 87.3 volts. The controller temperature is 23 degrees. The temperature sensor isn't connected, so this shows the motor temperature. Well, that's basically it. So now, perhaps we can check the throttle. So, where is it? Here it is. The throttle voltage is currently 0.87 volts. Pressing it now. The voltage changes, the throttle works. Now I want to check the buttons. Here, both O1 and O2 are at state 0, meaning the buttons are off. This one is the second, and this is the first. Yes, the buttons work. The power button works too. I've already preloaded the firmware onto a micro SD card. The display has a special port for it, so now I'll just insert the flash drive and start the firmware update process. We go into the device menu. There's only one controller here, but you can connect several. Now, settings. Oops, pressed the wrong button. So, settings and updates. Update firmware. That's it. I've basically connected everything, reflashed the controller, check that the throttle works. Next, we can connect the motor and move on to the mechanical parts. Alexei will explain everything more clearly and understandably from here.
Hello everyone, my name is Alexei and today I'll tell you how the mechanical part of our drive for the test stand is built. We made the stars and the supporting frame using a laser. Then I machined the stars on a lathe, gave them a specific bevel and filed down all the sharp edges on both this star and this one. Next, I made the axle on a lathe and also made the bushing to which the star is directly attached. The bushing goes here. It was carefully pressed in using a press, then a hole was drilled through the shaft and the bushing. Afterward, a thread was cut into the axle, and it was then securely fastened in place with 2 screws to ensure it stayed firmly attached. Then Sasha very carefully and skillfully used a milling machine to precisely make the mounting seats, the robust bearing mounts into which the precision bearings were carefully pressed. Then the sturdy axle was gradually and securely pressed into the bearings, ensuring a proper fit. For a more secure and reliable fixation of the axle in the bearing, a special groove was machined for a retaining ring, and a retaining ring was installed on both sides, just like here. Then the entire frame was assembled and welded together. Special clamps were also made on the milling machine, which are put onto the lever of our scooter and are additionally secured from above with a plate. The sprocket, which will be installed on the motor, is fixed at the mounting point. There should be a cover here, but instead of the cover, we removed it and are installing the sprocket here. I'll show you how it fits in there. This is how the sprocket fits in. It is tightened with screws. That's it. And then the entire assembly is carefully installed onto the scooter. Chain tensioner. The main part of the tensioner was also carefully made on the milling machine. 2 ball bearings were precisely pressed into it, and the axle itself was skillfully made on a lathe. Special grooves for retaining rings were also made on the axle so that it fits tightly and doesn't shift or move in the bearings. The tensioner sprocket was also made on the milling machine. Then it was carefully machined and smoothly rounded on the lathe as well. The tensioner is installed right here, just like this, supporting the chain and ensuring that proper tension is always maintained throughout its operation. Just like that. See, it actually has some play or movement, and you can notice that it presses up like this. We used a standard H520H chain, and based on this chain, all the sprockets and the tensioner sprockets were designed.
I didn't really think through how we were going to assemble all of this, so now the 2 of us are trying to put it all together. Right onto the standard scooter. Well, it more or less worked out. Now we just need to get the wheel on with a hammer and a bit of brute force. Now this is the final moment. I want to drive the engine in all the way. The fit everywhere is really solid. Now, let's simply put in the end cap. Alright, let's do it. Yeah, go ahead, pull on the laundry.
We carefully assembled the wheel together with the axle, making sure that all components were properly aligned, which will then be securely attached via a coupling to the shaft of the test stand sensor. What did we use here? We made a chain tensioner and carefully aligned the sprockets to make sure everything was properly set up. Let me tell you about the chain tensioner, which has this kind of travel and is tightened from above with a screw. And in this way, you can create the necessary chain tension. We made the axle with seats for couplings on both sides so that it can be attached to the test stand from either side. Now I'm connecting the power wire to the power supply unit, which will in turn power our pump installed in the scooter. Let's take the pump. Here's our pump and these are its output wires. For clarity, let's remove the foam. That's just how the system is, so we simply connect it. Turning on the pump now. The pump has started operating, so what's the setup here? The pump draws fluid from the expansion tank, then pushes it into the motor, and after passing through the motor, it goes into the deck. In short, there are still some important questions about our cooling system, but we need to experiment further to fully understand its behavior and performance.
Okay, we've brought everything much closer to the test stand, and we've set the scooter up horizontally, so it can be properly and securely fastened without any misalignment or instability. Now I'm going to connect the battery to, well, the controller, and then from the controller to the motor, plus the throttle and the display. Basically, I'm going to assemble everything together, step by step. We'll start by connecting the controller to the power supply, both positive and negative terminals. I've made these terminals right here, so for this stand, I'll just screw them in place and cover them with heat shrink tubing so nothing gets shorted accidentally. We've connected the positive and negative wires, the phase wires, and now I'm connecting the Hall sensors and the temperature sensor. 6 wires in total, which are all essential for proper operation. And now, finally, I'm connecting the controller to the display, making sure every connection is secure and in the correct place. That's it. The controller is now fully connected and ready for use. Now I'm going to connect the throttle. Here we have the throttle lever, positive, negative, and signal wires. These are the buttons, which each have a negative and 3 contact wires. It's very convenient that everything is clearly labeled on the display, so it's quite hard to make a mistake during the installation process. This is the external power button, and these are 2 additional buttons. All the buttons are fully programmable, so you just need to connect them, and their functions are set up in the settings menu. And now, the throttle lever. Alright, this is a crucial and important moment. Everything is connected, and right now, we're connecting the power. Now the main thing is not to mix anything up. The capacitors are going to charge, so there might be a spark. Alright, let's just turn it on. The battery is almost fully charged, and the controller temperature is currently 21 degrees Celsius, while the motor temperature is at 22 degrees Celsius. The thermal sensor is functioning properly, which is definitely good news. First, we need to carefully set up the controller so that it works correctly and efficiently. The very first thing we'll do is go into battery mode. The maximum charge is set to 92.4, and we will set the minimum to 66. We have a 22S battery pack. So the maximum charging current will be 80. We'll set the discharge current to the maximum. The battery allows it. Let's set it to 400. We won't adjust the power settings. Next, let's move on to the motor settings. Now, for the temperature sensor, we'll set the maximum temperature to 100 degrees. The delta is the temperature difference at which power reduction will begin. I'll set the delta to 15 degrees, so when the temperature reaches 85 degrees, the controller will start cutting power. The number of pole pairs I have, 15, control mode. What options do we have here? Well, we have trapezoidal, off, and charger modes available. However, what we actually need in this case is the sine wave mode. For phase current, we will set it to the maximum allowable value, and for battery current as well, we will also set it to the maximum. As for speed, we will limit it to just 20% of the full range, and we will start our testing process from that point. Now let's begin the automatic setup procedure. Bring it up to